Hello folks, how's everybody doing? Hope you're doing fine with this coronavirus problem. I'm doing okay, as best as you can at my age. Anyways, we have an exciting day again today. I'm going to start with questions and comments. There were quite a few of those in different fields. So you'll get a feel for it one by one here. The first one has to do with politics. I don't usually do politics, but I just wanted to make a comment on that for those who are interested. Anyways, the first comment was like this, says, I wonder what Bill thinks of Snowden and Assange. Well, let me tell you what I think of these two bozos. Let's see if I can get this thing up here. I have an article that I wrote in Quora. What do you think is going to happen to Julian Assange now? And that was last year. And so you can look it up in Quora and you'll find out what I think of Mr. Assange and Mr. Snowden. In a nutshell, they're both U.S. government operations, okay, intelligence operations, okay, from different. You have to remember, the United States has 32 intelligence agencies. It's not only the CIA, that's the most famous one, but they've got 32 agencies, and the United States spends $82 billion, I think, a year for intelligence. That's a lot of money, more than the national budget of many countries. That's got to produce something. There's got to be a reason for that, okay? And you research that. Anyways, yeah, we're in the age of information, or what I call disinformation, really. And these are people with whom I, over time, have cataloged as disinformers. Okay, this is what I think of. That these are disinforming the public in one way or another. Either they're idiots, they're just too dumb to do their work, or they're disinformers. I have to believe that they are disinformers. I had direct contact with two of them, James Randi and with Tim Weiner there. And, you know, that's my conclusion. I make my own blacklist of who's disinforming the public. And all these people, to some degree, not all of them, but most of them have ties to intelligence networks and people. They get their information, they get whispered in one ear, and they're the mouthpiece. When the CIA wants to tell you something, they'll go through some of these people or some other reporter that they recruit. Anyways, that's my take on that, on these people. Here's one of these guys. Let me put this back up here. One of these individuals, the last guy here, he got out of reporting. Now he founded his own organization, and this is what it says: founded by a former NBC News investigative reporter, Jim Popkins, the Seven Oaks Media Group is a select group of former reporters from the nation's top print and broadcast news organizations who truly understand the news. I don't know about the news, but they do understand something about intelligence because they have the right contacts. We're trained to work quickly and efficiently in tight deadlines and can instantly access a vast network of contacts inside the media, on Wall Street, and all across Washington. It's all about delivering measurable results for your firm. So whether your organization wants to attract media attention or stay out of the headlines when the spotlight becomes too hot, why not trust media professionals who have been there and back? Yeah, good old Jim Popkins. He's the guy who broke the news on my buddy Rolando Sorraf Trujillo. Never heard of him again, right? And you never will. Anyways, here's good old Assange, and just one last piece here. This is a statement he made. It's out of the Wikipedia, the last line in the Wikipedia article on Assange. And here you can tell what side Assange is rooting for. And he says the following. He says, we treasure our strong Jewish support and staff, just as we treasure the support from pan-Arab democracy activists and others who share our hope for a just world. That's U.S. policy right there. So the people who least have a problem with Julian Assange is the United States government. No, in fact, everything that Julian has done so far has favored the U.S. government and gone against, especially Arab nations, Russia, China. So no, Assange is an asset. He's not, or something close to that. But he's not playing the game that he's supposed to be playing. But he plays his role quite well. He was trained for that. And Snowden is no different. They're on the news every day. You won't hear about people like April Gallup or Willie Rodriguez or some of those from 9/11. You won't hear about them ever again. They're not in the news. But these guys on the news every day. That should make you stop and think what their purpose is. Anyways, let's go with questions or comments on extinction. Here's the first one that I picked up. Okay. And it says, a square of soil, fresh air, and water. Yes, we can even do aquaponics in our living rooms to become self-sufficient. The issue is not so much self-sufficiency. That's not the issue. The issue is defense. 911, that's the issue. There won't be any 911 to save you, okay? And that's the real issue with what comes after the collapse. Once there's economic collapse, everybody's on his own, okay? And so it doesn't matter if you can grow stuff in your garden, you won't have friendly neighbors. And for sure, there'll probably be roaming bands and whatever. In fact, someone here put a comment also says something about the militias. It says, your extinction theory, I suggest you are confusing the collapse of current system and a lot of people dying with the dying of all people on Earth. No, I've had my theory for 20 years before the coronavirus. I obviously did not know that the coronavirus was going to come around. Irrelevant, totally irrelevant. The theory has to do with the collapse of the economy, and that's guaranteed. The world economy, the global economy, man's artificial economy cannot grow forever. When it stops growing, that's it. And now we have, I don't know if this coronavirus leading to it, it's just a beginning of what's going to happen in the next few months, or maybe it's just a blip in the charts. Who knows? We'll find out with time. For sure, after everybody or a lot of people go back to work, things are going to pick up again. There's going to be investment and so on. The question is whether it goes back to normalcy, to where it was before. That's a big question, okay? And that's the only role of the virus in that context, okay? I remind you that any organized militia can impose order locally. Yeah, the question is you have nothing to pay the militia with. These voluntary guys, that go out there, if they're starving, instead of militias, they're going to be robbing you and killing you. Again, maybe you should put that back up here. Where is it? This one here. Okay, if your neighbor does not follow the commandments, please call 911. Sure. So I don't know about the militias. And it says also there are isolated regions of the world that really are self-sufficient and difficult to get to. This place is big. Yeah, that relates to what people say is lost tribes. No such thing. All tribes have been found. Okay, no lost tribes, and people say, well, these don't belong to our economic system. It doesn't matter. The first people who will die are those lost tribes because they have no defense. They don't even know what's going on out there, and and they're being protected right now. Again, protection, defense is the issue. The Amish, they grow stuff every day, and they do very good jobs of growing product and so on. They're going to have to worry about defense. There will be no judges, no police, no National Guard. It'll be free for all. People will run over their farms and just do whatever they have to. Okay, so the problem is defense. Okay, it's very hard sometimes to see. Okay, I hope everybody can hear me okay over there. Anyways, let's continue here. Another comment on the issue of extinction. Yeah, I want to get those out of the way so we can get to Mr. Brian Greene today, right? And Here he says, Bill has already reneged on the time frame prediction of his extinction theory. Well, I don't know about time frame. Yeah, that's got to do with prediction, with religion, with my beliefs. That's different than the mechanism of extinction. And people don't always pick up on that, which is the only exciting part of it. Absolutely not true. In fact, someone answered him and beat me to the punch, and I'll put this up here. It says, no, the exciting part is not when, but how. Yeah, that's the issue. The issue is the theory of how mass extinctions occur, not when it's going to happen to man. And he said it was our lifetime part that was the best seller, but he took that back. No, I haven't taken that back. I think it's going to happen within our lifetimes. It's going to happen within this generation. I don't think we've got too long to go. That's my gut feeling. That's my belief. Again, that's part of religion. Okay, and starvation is a pretty obvious, unexciting, and unoriginal way for a species to eventually go out in some distant future. Well, first of all, it's not the pretty obvious, because not a single extinction theory says that humans are going to die because money is going to disappear and food will be no more as a result of that. That's the first one. You can look it up anywhere you want. You won't find that theory anywhere. The only place is in my book, okay, Why God Doesn't Exist. Unexciting, unoriginal way. Well, I don't know about exciting. Mother Nature's very unexciting in that sense. She doesn't have flashy, asteroids or volcanoes. She doesn't do extinction with that. She does it the humane way, with biology. Okay, and it is original in that sense, because no one has ever mentioned that money is going to disappear and that's what's going to kill man. Okay, but the underlying theory is that the economy, the ecological pyramid of any species for that matter, overturns, or a group of species overturns. When it overturns, the whole food chain that depends on that goes away. That's what happened to the dinosaurs. All the conifers disappeared primarily. In other words, what happened there, they had the, especially I think the cycads and the cycadioids, and those were on their way out. And that's what these dinosaurs ate. They also ate some Araucaria, and those also diminished in numbers and in species and in numbers within each species. So their world was collapsing. Their primary production was getting smaller and smaller and smaller. Their forests, their jungles were decreasing in size. I call them islands, and they were stuck on these shrinking islands. And at some point, a critical point, that's it. They were few in varieties of species, and also they were few in numbers within each species. In the seas, same thing. What disappeared were the foraminifera, the diatoms, especially the big ones, the ones that had been around for a long time. These were the dinosaurs of the seas, of the plankton in the seas. Okay, and they disappeared. In other words, their numbers shrunk to critical levels. And you had the ammonites, who were also declining in the number of species. And what did they eat? Well, they ate the foraminifera and the diatoms. And when their numbers decreased, well, the big guys like the mosasaurs, they hunted, they ate ammonites. And so the whole food chain collapsed in the seas as well. And it's a long story to explain why it happened simultaneously, or more or less simultaneously, with what happened on land. I'm not going to go into that, but I've covered that in my theory as well. So it's just, I'm not going to cover that point right now. Okay, so that's the issue of when. Yeah, that's it, I guess, for that. Okay, so let me get into Mr. Hassan, Mr. Hassan, and let's get into Mr. Greene, okay, and see what he has to say, especially about string theory. String theory is the newest version of mathematical physics. It attempts to merge, okay, you got to understand the global picture here. It attempts to merge general relativity with quantum mechanics. Are they trying to merge the physical interpretation? So-and-so, really not, okay? That has never been solved within general relativity or within quantum mechanics. Now, what they're trying to do is merge in other words, create an equation, a grand equation, what they call the grand unified theory, which is really the grand unified description, because it's not a theory. Okay, they're not referring to an explanation, a mechanism. What they're talking about is merging the equation so they have a single equation that describes, not explains, but describes all phenomena in the universe. That's their goal. And they're still working on that, and supposedly string theory is what's going to bring it all together. So we start with... Oh, I did have a comment here, a couple comments. I thought I had more. Let me finish these two comments here. One fellow says, because it serves as an introduction to what Greene does with string theory. Okay, it's a good introduction. So here it is. A fellow says, Tesla, to understand the universe, think in terms of energy, frequency, and vibration. I'm glad the fellow immediately answered with my take on that, and then energy has never been defined. We don't do frequency in rational science. Vibration is a concept. Yeah, I couldn't have said it better. So Tesla was dealing with concepts, with abstract concepts, and you cannot explain physical mechanisms with abstract concepts. We're going to get into that in a minute when we go with Mr. Greene, okay? And there was another comment here, okay, also related to mathematicians, okay? This fellow says, he says, I think you are too hard on mathematicians. Oh, okay. I'm such a bad guy, right, for not using bad words here. I look at mathematics as a purely description of behavior. That part, we don't disagree. Totally in agreement. It's just a description of behavior. Using a measured unit in which the units can be input, out, etc., etc., okay? For example, spreading a deck of playing cards on a flat tabletop, a hidden hand is moving and spreading the playing cards around. Mathematics is describing, measuring the amount of movement between the playing cards. No explanation to the what is moving the playing cards, just a description using a measuring unit. Yeah, essentially he summarized it quite well. All that mathematics does is describe. Mathematics has no power to explain. The problem comes in when you go into and put mathematical and you add to it the word physics, and you say mathematical physics. Now we're in trouble. Now we're in real trouble because mathematics has nothing to do with physics, physics with mathematics. Why? Because mathematics describes and physics is supposed to explain. What the mathematicians since the days of Newton have done is go through descriptions, and they call them explanations, and explanations are theories, so they talk about the theory of general relativity, the theory of quantum mechanics, string theory, and so on. These are not theories. Let me tell you what the problem is. They're not focusing on the physical interpretation. They don't care about that. Or like Richard Feynman says, physicists, so-called physicists, have given up on that. They're not interested in trying to explain or make sense of the universe. They've given up on that. No, what they do, they call theories just mathematical descriptions, equations. And that's all they publish. If you look at the so-called scientific literature, all you'll see is all these people talking about equations. And all they're doing is descriptions. So the problem is there, science is not descriptions. Science is explanations. And for that, you need to understand the difference between the two. And here I put a little definition there so that you can compare them. What is an explanation? The causes in physics, or reasons in the case of philosophy, underlying a phenomenon. And second definition, you could say how. A mechanism in physics, right? A consummated event happened. An explanation deals exclusively with the past. Science is only about consummated events. You have to explain what happened, how it happened, okay? And so there's a difference between a description and an explanation. And here's where we have the problem, because all these people, mathematicians, as I call them, they give you a BS explanation for some physical phenomenon, and they say, oh, that was a black hole. So what's a black hole? It's a bunch of mass in zero volume. Oh, okay, and you just walk away, and okay, that's what you guys concluded. You know, that's not a physical interpretation. I need to know how that mass, so-called mass, affects an object far away, such as a star, and compels it to go around that center of mass. We can't do this with concepts. We can't say that mass does this and mass does that. Mass compels a star to do this and that, and that's exactly what they have in at least in relativity. They have the same situation with dark matter. You know, what keeps the galaxy, spinning at a certain rate such that the stars on the outside go just as fast or faster than the ones on the inside, when it should be the other way around? Mass. They just sprinkle mass wherever they need it in the equation. They say, see, we fixed the problem. We fixed it with mass. Well, I don't care. I need to know, I need to understand the mechanism of what keeps that star physically bound to the center of the Milky Way. And unless you have a physical mechanism, you put an object there, we'll never understand your mechanism. And to say that mass does it, well, you haven't said anything. All you did is just a bunch of description, mathematical description. Okay, now onwards with Mr. Brian Greene. Here's the Wikipedia definition of what a string is, what string theory is about. So it says string theory is a physics theory, okay? I don't know about that. That the universe is composed of vibrating filaments of energy. Filaments of energy. Now, I wonder what that is when Mr. Richard Feynman says he doesn't know, or no mathematician on earth knows what energy is. We don't have a physical, we don't have a definition of energy, and we don't have a physical idea of what energy is. In other words, we don't have a physical object there, okay? I can't draw energy. Okay? You can't draw a picture because it's a concept. And you cannot say that a concept such as love or information does this or that. And that's what they're saying when they use energy. Energy is just another word for spirit. And, the mathematicians, they didn't want to use the word spirit because they say, oh, that belongs to religion. People are going to say or think that we're doing religion. So we're going to call it energy. That sounds a lot more scientific. Okay, these strings of energy, whatever that is, right, represent the most fundamental aspect of nature. The theory also predicts other fundamental objects called branes, okay, and we're going to go lightly over that one as well. All of the matter in our universe consists of vibrations of these strings, okay, so they have these strings and they vibrate, okay, and what those are supposed to be, the vibration of that string locally is supposed to be a particle. Okay, and so you got the strings over here and you got the fields over there. See, the way quantum sees it, it's the fields of general relativity. Those fields are vibrating and those fields are the particles. These guys are saying, no, it's not the fields. Remember, the fields are extended. They're all over the universe. So you have one field and it covers all the way to the edge of the universe. Locally it vibrates and that field is supposed to be a particle. String theory says, no, forget about all those fields. We don't care about all that. We have a string, a one-dimensional filament of energy, one-dimensional filament string, one-dimensional line. But this line is elastic and it vibrates. Okay, so it's vibrating, and that's a particle. So we have the vibration of the field and we have the vibration of the string. Okay, keep them separate because one belongs to quantum mechanics, the other one belongs to string theory. One important result of string theory is that gravity is a natural consequence of the theory, which is why scientists believe that string theory may hold the answer to possibly uniting gravity with the other forces that affect matter. In rational science, there's only two forces. That's push and pull. There are no other forces. But the mathematicians had to invent two more forces. One, the gluon, which is the strong force, and the other one is the weak force, the W's and Z's. So they created these new forces. What is the gluon? It's a pull force. What is the weak force? It's a push force. So we're still back to push and pull. And I don't think there's any mathematician on earth that can conceptualize any other form of physical contact other than push and pull. So this nonsense about four horses of the apocalypse or whatever they have in quantum is absolute poppycock. All right? Has no place in science, but that's what they have. Okay, so what was the problem? Why did they have to go to string theory? I mean, if quantum has been verified and proven and demonstrated and whatever and verified and falsified or unfalsified, right? And general relativity has been unfalsified, proved, everything works right. Why did they have to go to string theory? Well, one of the reasons was that the new generation of mathematicians coming out of the universities had nothing to work on, because if quantum solved every problem already, you know, who was it? Niels Bohr said it's a complete theory when he was challenged in 1936, okay, by Einstein. 1935 was Einstein's paper, and the reply was 1936 by Niels Bohr, something like, can quantum theory be considered a complete theory, or something like that. That's the name of the paper. Anyways, Einstein, who'd never believed in quantum mechanics, he challenged the notion that Niels Bohr had that quantum was a complete theory. He said, you know, it's not complete. And the answer was, yeah, it is complete. So if quantum is complete and general relativity is complete, we're done, right? We're done with physics. So what does the new generation do? Well, they said, well, you know, these two theories, they don't talk to each other, you know, especially on the issue of gravity. Quantum has a particle called the graviton, and it carries a force. That's the term, carries a force of attraction, I guess, right? And the other one, general relativity, says, no, it's warped space. That's what gravity is. And so we have two different mechanisms and two different sets of equations for each one of these so-called theories, okay? And so that's why they had to merge them, and that's what the new generation is working on. All these people coming out of college who didn't quit because they didn't, you know, those people who realize that it's all nonsense, they quit and go into engineering or some other thing. But these guys, the guy who stays, he stays for two reasons. He wants to get a job, you know, he wants to be placed in a good position in the future, his career. He wants to be working at NASA or at CERN or Fermilab or SLAC in California. So they want good jobs, and that's one of the reasons they continue. The other one is, you know, all they have to do is just memorize the answers on the test, and as long as they answer what the professor wants, they pass, and they also will get an advisor for their PhD. And that's why the only people who make it through the line are the yes men, the people who just bow down to what was discovered or the catechism that they had to memorize from the previous generation, which learned it from the previous generation, and so on down the line. So now they're working on string theory. And string theory, again, all they're doing essentially is saying that particles are vibrating strings instead of what quantum proposes, which is vibrating fields. And of course, there's going to be those people who are going to try to associate fields with strings and strings with fields. Obviously, that's part of the game, right? Okay, and yeah, and so one of the issues was they had so many particles coming out in quantum, and here you have Mr. Greene in his little show, The Elegant Universe. He put this particle zoo. He said, look, this is what we have. We're creating particles every day. We're inventing new particles. We're giving them new properties. And, you know, when's this all going to end? And so with the string theories came out, they said, look, all these are really different vibrations of the string. That's all it is, of that one-dimensional filament of energy, okay? And just to show you how ridiculous mathematical physics has become, here's supersymmetry. This is you could say, a branch of quantum mechanics. And look at all the particles they had to invent. They invented parallel particles. And to distinguish them from the original particle, they put an S in front of them. So here's the Here's the rundown. All what these people do for a living. This is what you're paying for. Under supersymmetry, the corresponding bosons and fermions are called superpartners. The superpartner of a standard particle is called a sparticle. Because none of the existing particles are superpartners, this means that if supersymmetry is true, there are twice as many particles as we currently know about. So now we're inventing new particles, just giving names to new things that we don't understand, or these guys don't understand, right? For every standard particle, a sparticle that has never been detected experimentally must exist. The detection of sparticles will be one of the key pieces of evidence the Large Hadron Collider will look for. And there you have it. You have the standard model on the left, and then the superpartner on the left. So you have the lepton and the slepton, and the muon and the smuon. And like the wino, that's the one I'm interested in. The W bozo becomes a wino, okay? And the zyno, I guess. I mean, what is this? What is this nonsense? What is this? I mean, this is all these people do for a living. They just invent names and they say, well, you know, theoretically, our theory predicts that there should be more particles, a parallel set of particles, and we're just going to put a little s in front of them and just call them sparticles. That's what you're paying for. That's, you know, these guys, remember, these guys are supported by government. Okay, you're paying for this one way or another, whether here in Europe or in the United States or in China or in Russia, those Japan, those countries that have, you know, accelerators and so on. This is what they're working on. They're all in contact with each other. Say, hey, why don't we call this a sparticle? Oh, okay, let's go with a sparticle. Okay, and so here's Brian's definition of a string, just to show that he's more or less in line with what the Wikipedia says. Tiny vibrating strands of energy called strings. That's what they are. Tiny strands of energy. Okay, that's what they look like, more or less, or that's how they visualize them. And you can see they're just closed loop. Okay, and all these particles are apparently loose. Okay, so the important part here, I want you to remember, they're all loose. Okay, they're all discrete. Okay, they're not bound to each other. They're all separate. Okay, you can see it here. I want you to make sure that you understand that part. It's going to be important because nothing has changed. All they're doing is saying, look, this discrete particle, all we're going to do now is say that instead of being a vibrating field, we're going to have a vibrating string. Okay, fine. So what's the mechanism of gravity? Okay, that's what we're going to work towards here. We're looking at a unification of general relativity with quantum mechanics. And where's the unification? In gravity. That's where you got to put your attention in. Okay. Okay. So here we have what is this one? Yeah, this is what he's saying here is that the particles are made of strings again. Just another version of it. Okay, I want you to see the protons are made of quarks, which in turn are made of strings. Okay, and that's what they look like, more or less, just vibrating things there. That whatever that thing is, a one-dimensional, they say it is. Okay, and so yeah, what you have is the atoms are made of protons, and protons are made of quarks, and quarks are made of strings. That's essentially what Brian Greene is saying. That this comes out of his documentary. Okay. So I'm not putting words in anybody's mouth here. Okay, what's another difference between QM and, in other words, here what we're trying to do is figure out what string theory is attempting to do. And what they're trying to do is merge quantum with general relativity. And you say, well, how do you do that? I mean, one is a spreadsheet, you know, this sheet, this canvas, which is supposedly smooth, and what quantum does says, look, at the quantum level, at the small, tiny level, at the Planck length level, right, and Planck time level and all the Plancks that they've invented, at that small scale where we can't measure, we can't really see in there, we can only theorize about it, very convenient, no? And what they say, at that level, space-time is not smooth. In other words, it's got this what they called quantum foam. In other words, remember, space-time is made of events. That's the theory. Okay, they say, look, space-time is built with all these events. Each event needs 4 coordinates. Three dimensions that you already know, length, width, and height. And the fourth one, supposedly time. So now we have a four-dimensional event, okay? And that's a point in space-time. And according to relativity, that's a smooth sheet. Okay, it's a smooth sheet, and or you can say a smooth fishnet, as is always shown. And each knot in the fishnet is one of these events. Okay, what quantum says, look, when you go with your microscope, your super powerful god-like microscope, and look at that same knot, it's not smooth. It's vibrating, and it's not even, and it's unpredictable. Remember the uncertainty principle from Mr. Heisenberg? Okay, so it's unpredictable. We don't know what happens at that point, and there's all this fuzziness. And here's what they try to show, you know, the difference. This comes again from Brian Greene's documentary. It says, our jittery, unpredictable picture of space on the subatomic scale and our smooth picture of space on the large scale. So those are the difference between, you can see the smooth general relativity sheet there, and quantum mechanics, all fuzzy, right? And what happens? What they're saying is quantum differs from quantum. We can interpret general relativity in terms of quantum if we can show that each one of those knots there, or each one of those lines on the right hand side in general relativity, is with all this fuzziness, has all this fuzziness in there. So what they're saying is we're going to build this quantum fuzziness in each one of the events of general relativity. Okay, if that makes any sense to you. Okay, and so. This is what they're working on. This is the idea of string theory, trying to show you that, you know, that the sheet, the space-time sheet, is not smooth. That it's got this fuzziness. How that affects gravity, I don't know, because what is gravity according to general relativity? Well, you have a bowling ball sitting on top of space-time, pushing it downwards by force, obviously, which they say doesn't exist. So here's the bowling ball weighing down the sheet, right? The fishnet, and how the fact that each knot in that fishnet is not smooth and vibrates and who knows what else? Who cares? What does that have to do with the mechanism of gravity proposed by Einstein, which is, you know, ball weighing down, depressing space-time, and something falling in there? What does the micro level have to do with that? Well, the way it got in there is through the black hole. Okay, because the black hole, remember, is also an event, one of those points in space-time. It's a singularity. And what's a singularity? Well, it's a no volume, infinite mass point, if you can call it a point or whatever that is. Okay, there's a hole in space, in space-time or space, both. So you got this little zero-dimensional hole. I don't know if Bugs Bunny can fit through there, but you got a zero-dimensional hole in there, right? And what these folks are saying is, we're going to analyze that little point, okay? And that's why the black hole kind of triggered string theory, because here was a chance to introduce quantum mechanics, right? The world of the very small into the singularity, right? They were able to say, oh, we can introduce some of the equations of quantum mechanics and try to analyze that singularity, that hole, which builds up space-time as well. Because, you know, black holes are so popular, and so they had to find some work to do, and that's what they're doing now. They're saying, okay, let's analyze the black hole, the singularity, the zero-dimensional hole in space-time. Okay, that's the idea. That's how quantum got merged into relativity. That's how it was brought in. That's how the subject matter came into being. Okay, and the new generation pounced upon it because they say, hey, we got nothing else to work on. We might as well work on this nonsense. Okay, and here's another version of the space-time sheet. Okay. And here it is. It says, tiny curled up circular dimensions. This idea that extra dimensions exist all around us lies at the heart of string theory. And says the mathematics of string theory demand 6 extra dimensions twisted and curled into complex little shapes. So one of the issues that they had to solve to get string theory going is that they had to introduce dimensions, many dimensions, okay? So they were not satisfied with the 3 that we are sure exist, or the 4th one that Einstein introduced, which was the time dimension. Really, it was introduced by other people who created relativity, the principle of relativity. And what happened? What general relativity says is that, you've got this point there in space-time, okay? And what these people did was just analyze that point. And how did they do it? They said, well, we're going to need extra dimensions. And they needed that for string theory to work. And so if you look at string theory, it has about 30 years of history now, at least 30 years. And what they've done is they've gone not only to 6 dimensions, they've gone to 10 dimensions. I've heard even 11 dimensions, 26 dimensions, and then they brought it back down. So they're working on the dimensions. It's like I say, it's proportional to the number of beers these people drink, okay? Because they just keep coming up with dimensions to fix a problem that I don't even know if they know what they're doing, because even if they fix it, let's say they come up with a equation that they need, whatever it is, I don't care. How does that change the fact that we have bowling ball on canvas explanation in general relativity? How does that, how will quantum mechanics explain that differently? Are we going to say that the pen falls to the floor because there's a singularity that attracts it? That there's a hole in the space-time locally here? Well, the general relativity obviously says that's not what the theory says. Their theory is that the rubber sheet, only works at the macro level. It doesn't work here on Earth. You can't use general relativity here on Earth, okay? So whenever someone, like there's a couple people on YouTube who do general relativity here on Earth, says, look, I can do it here in my basement. What they're doing is they don't understand the theory. The theory says that it only works at the macro level. And so no matter what quantum does stands on its head, it will not fix that problem, because the explanation, the mechanism that general relativity proposes is ball on canvas. That's what it is. That's their physical interpretation. And that's at the macro level. You can't, the fact that black holes have a singularity, and that could be a topic for quantum mechanics to, flow into general relativity, it still won't fix the problem of bending space-time and having something drop in there, because that's macro type of phenomenon, okay? And so, the question is, are they just spinning their wheels with these equations just to show how smart they are and that they can handle the variables and numbers and so on? It's really a waste of time and waste of energy, but we don't know what energy is anyways. Okay, so what is the explanation for gravity? Because that's the bottom line. We want to explain gravity, okay? And what was the deal with string theory? String theory says that particles are vibration of strings, one-dimensional strings, one-dimensional filaments of energy, right? Okay, so if that's what particle is, that's what the graviton is. And what is the graviton? Graviton is the particle proposed by quantum mechanics that serves as the mediator between two objects. If the pen falls to the floor, it's because the Earth attracted the pen downwards. How did it do it? Well, it sent gravitons. It sent gravitons to the pen, and somehow the pen received negative momentum, and it was attracted downwards towards the Earth. So they're still working on the issue of negative momentum when they talk about strings being the vibration of springs being what a graviton is. If a graviton is vibration of a string, we haven't solved anything. All they did is talk about the structure of the graviton. They're still not addressing the mechanism, the irrational mechanism that quantum has already for attraction. Okay, which is with discrete particles. You throw a stone at the donkey and the donkey comes towards you. And you say, Bill, you're putting words in their mouths. Okay, here it is. This is Brian Greene's documentary, okay? I didn't put this in his words. You'll see them here, okay? And here it is. He throws the ball to the other guy, and look what happens to the two players, okay? They are they are attracted towards each other because they're throwing the ball at each other, okay? The forces carry negative momentum. These guys are attracted to each other simply because whenever they throw the ball, it just throws negative momentum. Negative meaning that motion is in the direction opposite to the flow of the ball. Okay, if the ball goes, instead of pushing the guy away, it draws him towards him. And again, if you think that I'm inventing all this stuff, here's more proof, more evidence. Okay, here's Mr. Baez, John Baez, in his physics fac at the University of Riverside. He illustrates that for us very well with his words. He says, if the momentum transferred by the wave points in the direction from the receiving particle to the emitting one, the effect is that of an attractive force. So you throw the ball and you pull the guy over, okay? So, again, you can see that, you know, I'm not inventing all this stuff. This is official from their websites. Here's another version of that. Mr. Victor Stenger, he's a professor at the University of Hawaii, quite popular he was. I think he died a couple years ago. And he says the same thing, but he does it with time. He says the vacuum is capable of producing interactions between particles at effectively space-like separations. Okay, and talks about the quantum fluctuations. And he said, let me explain. No doubt the idea of motion backward in time makes a grievous assault on common sense. No kidding. However, to a particle physicist raised on a diet of Feynman diagrams, motion backward in time is not all that disturbing. Okay? So these guys are talking about motion backward in time. They're talking about negative momentum. And this is what string theory is going to pick up on. That's how they're going to explain gravity. They're going to say, well, what's really happening is we have negative momentum. The graviton goes forward and pulls the object towards you. And then the only thing that string theory is trying to address is what the particle is made of, which is irrelevant, totally irrelevant. And they say, look, it's a vibrating string, so who cares? I want to know what the mechanism, how do you pull by throwing discrete particles? And they say, well, we do it by mathematics. We put a negative sign in front of, something like the Yukawa equation, and suddenly, you have negative motion. You have motion towards you. And I want everybody to try this at home. Do it as a homework. Go to your kitchen, and throw your tennis ball at the pot or the pan, okay, and see if the pan comes towards you. Okay? That's what these people are saying. But they say that the quantum world works differently than what works in your kitchen. No kidding. Yeah. Okay, and here's a final point on that. Here's how we rip space-time. Remember the black hole opens a hole in space-time, right? And so for this, they need these branes. What are these branes? Well, it says strings actually make it possible for space to rip. Okay? And so how do we fix it? Well, we fix it with these branes. And what are these branes? Well, it says, as a single string dances through space, it sweeps out a tube. The tube acts like a bubble that surrounds the tear in space-time, right? So it surrounds it. What they're talking about is time there. They're talking about a string moving through time. And when it moves through time, this contrail that it leaves behind its butt, it becomes a tube, a physical tube. So, so they say these tubes become branes, and these branes move, and when they move, you have the string turns into a brane because it creates a surface, right? So now we have this brane that suddenly it's not a circle. Now it's a what is it? It's a plane. In other words, it's not a circumference. It's now a circle. The circle moves, and by doing so, it creates this tube, and this tube fixes the holes in space-time created by stuff like black holes. My God, what have they done to physics? These people really gone a little overboard with their equation. Okay, so what are some of the problems, the fatal problems with string theory? Why it's not even it's a non-starter. It's not even worth starting with this. Let's see if I can get this thing up here. And here it is. Let me put it on here. These are the fatal requirements of string theory. It ends up predicting massless particles. It invokes extra dimensions. It created the virtual particles. It had to make virtual particles more real than the real particles. Now they talk about virtual particles. What's a virtual particle? Is one that comes out of the magic wand of the mathematician when he needs it. When he needs it, this particle just comes in from the void, pops in from space, right? And comes into the world, does whatever it has to do to solve the equation, then goes back and disappears, supposedly. I mean, I don't know what disappearing means in quantum mechanics. Does it turn into nothing? Not really, because it goes back to being space, and space is not nothing according to them, so we never have nothing. So it's like it comes from this invisible world of space into the visible world. In fact, it's not even visible in our real world. It's just an ad hoc particle that has to be put in there momentarily for the equation to come out right. Then it goes back and does whatever it wants. So virtual particles are, very handy to a mathematician because he can put them in any equation whenever he needs it. He just waves his magic wand and says, abracadabra, it is so. Okay? And then they invented tachyons, particles that travel faster than light. They had to have that, and they said, well, no problem. It's just that tachyons come from the future. That's how fast they are. They're already coming back when you're still going forward. I mean, if you think, mathematical physics has any rationality whatsoever today, well, it means you're not in tune with what's going on out there. Okay, I want to address a question that came out, one of the comments also, one of the persons out there, and I thought it was important in the context of not only string theory, but quantum mechanics and general relativity. And it's, here's the comment. Let me get it up here. Okay, and it says, how does Greene's explanation of gravity oppose the rope hypothesis? When the sun disappears, in other words, when the ropes connecting the Earth and the sun is cut at the sun, does it not take time for the information to travel along the rope as a wave before it reaches the Earth? If you spun a ball around with a long rope and then you cut the rope, does the ball stop orbiting instantly? In other words, is there time involved? And the other day I couldn't find it, but here I found it now, my little ball. Let's see if I can get this thing out of here. Okay, and here you see it. Okay. That's how I'm saying the sun twirls the Earth around, okay? We're connected to the sun. Every atom of the sun is connected to every atom that comprises the Earth, okay? So the sun swings the Earth around itself. So the question is, if there was a rope tying the Earth to the sun, a physical rope, right? Let's just talk about the regular rope that you buy at the hardware store. Let's say you had a rope. If you cut that rope, the question is, does the Earth fly out instantaneously if that's the only thing holding it to the sun? Or does it take time for that information to reach, the Earth? And so here's a thought experiment that I create so that you can put this in the right context. And it's got to do with what I discussed the other day. First, let's go with that. Here's Newton's version of gravity, which is instantaneous. Okay, if the sun were to disappear, all the planets would fly out instantly. Okay, that's what his equation suggests. Mass over distance squared. Okay, the sun disappears, blip, somewhere, blip. Where's the blip, 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 blip? Give it a second here. There, blips out, planets fly out instantly. Okay, that's Newton's version of gravity. Okay, his equation. Here's Einstein's version, and according to Greene, it takes the sun. It would take the Earth. It would take the signal. To reach the Earth. It would take about 8 minutes if the sun were to disappear. Okay, so if the sun were to disappear, the Earth would still be rolling around nothing for another 8 minutes until it finally realizes that, the sun is gone. Okay, so that's their version. And, you may want to buy their version. I don't buy it. And so again, here's a little thought experiment which I made. Let's imagine we have our universe, okay? And in this universe, what do we have? We have Andromeda Galaxy on the upper left, and we have the Milky Way on the lower right, okay? So this is the homework that you're going to have to do to figure out how you view this, okay? Okay, we're going to put two people, and they're 2 million light years apart, okay, in the middle of space there. You can put them on a planet if you want, whatever. Okay, so they're 2 million light years apart, and they're doing a tug of war. In other words, these guys are pulling against each other, and there's tension on that line, okay, because they're pulling one against the other. Okay, straightforward. Okay, what happens if some little fella, okay, comes in there and suddenly cuts the rope? Okay, puts a scissor and cuts the rope. Will these guys fall backwards instantly, or will it take millions of years to discover that, oh, the rope has been cut and the information now took, I don't know, 1 million years to reach me? Which do you think? Do you think you would go with math, which says that, or would you go with the physical part, which is you're connected to nothing now? You're not connected to the other fellow anymore, okay? So here's the rope, okay, just so you see where I'm coming with this, and the rope is cut right there in the center, okay? The rope is cut. And so the question is now, will they fall backwards instantly, or will it take 1 million years for the information to reach them along the rope? Okay, here's the rope version, the irrational version of this. Those two guys should fall backwards instantly. Okay, there should be no time delay because now you're not connected to anything. In other words, that rope is just floating in midair. Why would it take 1 million years for the information to reach you? Okay, and here's the Einstein version. Okay, is that what it would take? It would take 1 million years for that rope to uncoil itself until it reaches you? Is that what these people are suggesting? Well, that's the homework for you to figure out. You figure out which version you like the most, okay? It's up for you to think about it, okay? Under the rope model, here we have the sun twirls the earth around itself. We can't cut those ropes. They're uncuttable, okay? The ropes, the underlying hypothesis for the rope is the single thread hypothesis, which means that all the rope, that there's a single thread in space. That's all there is, okay? And it's this thread that turns into ropes and into atoms, okay? So that's our universe. That's our entire universe. Very simple universe. And yeah, if that's the case, you can't cut the rope. But if somehow you were to cut the rope, you can see that the physical mechanism that holds the earth to the sun would instantly, disappear, and there's no reason for the earth to roll around the sun. And so this notion that Brian Greene has that, if the sun were to disappear, we would not immediately get flung out of the solar system. It would take, 8 minutes? It's the same situation as the two guys, doing tug of war in the middle of space. If someone cuts that rope, and that's the only thing holding them together, right, in the universe, right? They're pulling on each other, and someone cuts the rope. Will it take 1 million years for them to fall on their butts? And again, either you take the mathematical version proposed by Brian Greene, or you take the rational version, which is you would fall instantly. And you can do this, prove it to yourself. Just go to the mountain and have someone cling from your rope while you're going up the mountain, and just cut the rope and see how long it takes for the guy to fall. Will it take 10 seconds because he's 10 seconds away or whatever? Will it take 10 seconds for the information to reach him, or will he fall instantly? With that, I'll see you next time, which is this Wednesday. We'll see you then. Bye-bye.